Right now, beneath your feet, the Earth is spinning at over 1,000 miles per hour, orbiting the Sun at nearly 67,000 miles per hour, while our entire solar system races around the Milky Way at almost 490,000 miles per hour, and yet you feel completely still. That stillness is the greatest illusion of your life. Most people will sleep tonight never realizing they are traveling through space faster than a bullet ever could. But you are here about to see what they don't. Welcome to Velarin, Sleepy Space Mysteries, where we slow down the universe just enough to feel its hidden motion. Tonight, we uncover why everything spins, why you cannot feel it, and why that silent rotation defines time, life, and existence itself. If even one quiet thought here brings you wonder, gently like this video, subscribe, turn on the notification bell, and join our membership to keep this small universe alive. And before we drift deeper, tell me in the comments where you're listening from tonight. I want to see how far the spinning world carries these quiet stories. Let us drift back further than memory, further than light, further than even atoms. Imagine time not in seconds, but in fractions so small they almost refuse to exist. 10 to the power of minus 43 seconds after the Big Bang. That is 1 divided by 1 followed by 43 zeros. This earliest moment is called the Planck era. In that brief instant, the entire observable universe, all that would one day stretch across 93 billion light-years, was smaller than a single atomic nucleus. We do not yet possess a complete theory that unites gravity with quantum mechanics at that scale. Our equations fall silent there. But even in that silence, something important may have already been present. Motion, not added later, not switched on, present from the beginning. For 13.8 billion years, the universe has been expanding, cooling, structuring itself. Yet when we look at the faint afterglow of its birth, the cosmic microwave background, we see something remarkable. This radiation, released about 380,000 years after the Big Bang, fills all of space. It is astonishingly uniform. The temperature is about 2.7 degrees above absolute zero everywhere we look. But not perfectly uniform. There are tiny differences, variations of only 1 part in 100,000. If the average temperature were like 2.70000 degrees, the variations would be about 0.00003 degrees. Almost nothing. And yet, those minute ripples are everything. Those slight anisotropies, those subtle uneven patches, are the seeds of galaxies. Where the universe was a little denser, gravity pulled more strongly. Over millions of years, those slightly denser regions collapsed into stars and spirals and clusters. Without that 1 part in 100,000 difference, the cosmos would be smooth. No structure, no rotation, no life. But some cosmologists noticed something even stranger hidden in those ripples. When mapping the cosmic microwave background across the sky, a faint large-scale alignment appeared. A pattern that seemed to point in a preferred direction. It was half-jokingly named the axis of evil. Not because it was dangerous, but because it challenged our expectation that the universe should look statistically the same in every direction. If this alignment is real and debate continues, it may hint that the early universe possessed a subtle global orientation. Not a violent spin like a top, but a gentle inherited twist. A bias written into spacetime itself. To understand how such a bias could arise, we move forward slightly in time, to around 10 to the minus 35 seconds. A blink within a blink. This is when inflation may have occurred. In 1981, physicist Alan Guth proposed that the universe underwent a brief, explosive expansion. In far less than a trillionth of a second, space itself expanded faster than the speed of light. Not matter moving through space faster than light, but space stretching. Inflation explains why the universe appears so smooth on large scales. It stretched out irregularities, flattening spacetime like pulling the wrinkles from fabric. But inflation also did something else. It took microscopic quantum fluctuations, tiny random jitters in energy that occur naturally even in vacuum, and stretched them to cosmic size. At quantum scales, fields are never perfectly still. They fluctuate, they shimmer. During inflation, those microscopic fluctuations were magnified to astronomical proportions. A tiny variation smaller than a proton became a region spanning millions of light years. If even the smallest of those fluctuations carried angular momentum, even the faintest twist, inflation would have preserved and expanded it, not creating spin from nothing, but amplifying what was already present in quantum uncertainty. Some experiments have searched for evidence of this early twisting. One clue may lie in something called B-mode polarization. When light from the early universe scatters off electrons, it can become polarized, meaning its electric field vibrates in a preferred direction. Certain swirling polarization patterns, called B-modes, may be fingerprints of primordial gravitational waves. Gravitational waves are ripples in spacetime itself. If inflation generated gravitational waves with rotational characteristics, they would leave behind a faint curling signature in this ancient light, a fossil record of the universe's first motion. Though measurements remain delicate and difficult, the possibility is profound. The idea that within the faint microwave glow surrounding us, there may be encoded evidence that the cosmos began not in perfect stillness, but in subtle rotation. As the universe expanded and cooled, matter began to form. Quarks combined into protons and neutrons. A few minutes later, simple nuclei formed. Hundreds of thousands of years later, atoms appeared. And through all of this, one law quietly governed every scale. Angular momentum is conserved. Angular momentum means that if something is rotating, it will continue rotating unless acted upon. And if a rotating system shrinks, it spins faster. You have seen this in figure skaters. When a skater pulls her arms inward, she spins more rapidly. No external push is needed. The motion intensifies because angular momentum must be preserved. In the early universe, clouds of matter began collapsing under gravity. As they contracted, they spun faster. Every galaxy, every star, every planet inherited rotation not because someone started them spinning, but because contraction amplified pre-existing motion. In 2011, Researchers analyzing about 15,000 spiral galaxies at the Harvard-Smithsonian Center for Astrophysics found a subtle imbalance in the direction galaxies rotate. Slightly more spirals appeared to turn one way than the other. The effect was small but intriguing. If confirmed, it might suggest a primordial handedness, a bias inherited from the earliest moments of cosmic history. The important thing to notice is this: nowhere in this story is rotation introduced from outside. It is never added as an afterthought. It is inherited, preserved, amplified. When we trace spin backward through time, from galaxies to protostars to collapsing quantum fluctuations, we do not reach a still point. We reach a deeper motion. The universe did not learn to rotate. It unfolded from a state where perfect symmetry had already been slightly broken. And in that tiny break, motion became inevitable. In the next drift of our journey, we will explore that broken symmetry, how the four fundamental forces separated, how matter gained a tiny advantage over antimatter, and how one extra particle in a billion allowed everything you see to exist. For now, simply rest in this thought. The first cosmic turn may have occurred before light, before atoms, before time as we experience it. And every rotation you witness today is a continuation of that original inheritance. As the universe continued expanding beyond that first fraction of a second, it did not cool smoothly like water settling in a glass. It cooled through transitions, through subtle shifts in symmetry. In the earliest instance, the four fundamental forces we know today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may once have been unified as a single interaction. At temperatures beyond imagination, distinctions did not yet exist. There was no separate gravity, no separate electromagnetism. Only one coherent field governing everything. But as expansion stretched space and lowered the cosmic temperature, that symmetry fractured. Around 10 to the minus 36 seconds, gravity may have separated from the unified force. Later, the strong force split from the electroweak interaction. And by roughly 10 to the minus 12 seconds after the Big Bang, the electroweak force itself divided into the electromagnetic and weak nuclear forces we observe today. Each separation was not violent in the way we think of explosions. It was more like a phase transition, like water freezing into ice. When water freezes, the symmetry of liquid motion is broken into crystalline structure. Something similar occurred in the early universe. And when symmetry breaks, tiny imperfections are amplified. Those imperfections carry direction. They carry motion. One of the most important transitions involved what is now called the Higgs field. Before about 10 to the minus 12 seconds, particles may have moved at the speed of light, effectively massless. But as the universe cooled below a critical threshold, the Higgs field acquired a non-zero value everywhere in space. Imagine a field filling the entire cosmos, and at that moment it turned on, settling into a stable state. When it did, particles interacting with it gained mass. Mass meant inertia. Inertia meant resistance to change in motion. And resistance to change meant rotation could persist and matter could clump. Without this symmetry breaking, matter as we know it would not exist in stable form. Motion would have no anchor. There is another asymmetry even more delicate, and perhaps even more essential. In the earliest moments, matter and antimatter were created in nearly equal amounts. For every particle of matter, there was an antiparticle with opposite charge. When matter and antimatter meet, they annihilate into pure energy. If the balance had been exact, everything would have vanished into radiation. No atoms, no galaxies, no planets. But it was not exact. For roughly every 1 billion pairs of matter and antimatter particles, there was one extra particle of matter. Just one. That tiny excess, 1 part in a billion, is why anything exists at all. After annihilation erased the pairs, that small surplus remained. All stars, all galaxies, every breath you take is built from that slight imbalance. In 1964, experiments revealed that nature does not treat matter and antimatter with perfect symmetry. This phenomenon is known as CP violation. It means that under certain conditions, the laws governing particles are not mirror-perfect between matter and its opposite. The effect is subtle but measurable, and it tells us something profound. The universe prefers a direction, a slight bias, a handedness. That preference may be intimately connected to the inheritance of motion, because in a perfectly symmetrical universe, every spin could cancel its mirror. Every rotation could be undone. But when symmetry breaks, cancellation is incomplete. Motion persists. Consider again the principle of angular momentum conservation. If a region of gas begins with even the faintest net twist, gravity will not erase it. As that gas collapses, the twist intensifies. A diffuse cloud becomes a rotating disk. A rotating disk fragments into spinning stars. Each star forms with its own rotation. Around those stars, disks of dust spin and condense into planets. Those planets rotate because the disk rotated. The disk rotated because the cloud rotated. And the cloud rotated because tiny asymmetries in the early universe carried angular momentum forward. When we observe spiral galaxies today, we see that rotation is not rare. It is universal. Billions of stars orbiting a common center in graceful spirals. The Milky Way itself completes one rotation roughly every 230 million years. That means since the age of the dinosaurs, our galaxy has not even completed a single full turn. Yet its spin has persisted for billions of years. Nothing had to keep it going. Once established, rotation continues in the near frictionless vacuum of space. If there was a primordial bias, however slight, inflation would have stretched it to cosmic scale. Symmetry breaking would have preserved it. Angular momentum conservation would have amplified it. And structure formation would have locked it into galaxies and stars. This is why rotation does not appear suddenly later in cosmic history. It is visible from the earliest galaxies we can observe, formed just a few 100 million years after the Big Bang. They already show organized motion. They did not learn to spin over billions of years. They inherited it almost immediately. The age of the universe is about 13.8 billion years. Over that immense span, stars have formed and died. Galaxies have collided and merged. Black holes have grown. Yet throughout all of it, the total angular momentum of the universe has been conserved, transferred, redistributed, but never destroyed. The spin of a collapsing star becomes the spin of a neutron star. The rotation of merging galaxies reshapes into new rotational patterns. Motion flows forward through time like a conserved thread. Broken symmetry made this possible. If the forces had remained unified, if matter and antimatter had annihilated perfectly, if fluctuations had been zero, there would be no rotation to inherit, no gradients for gravity to amplify, no direction for time to follow, because time itself depends on change, and change depends on asymmetry. So when we ask where spin began, the quiet answer emerging from physics is this: it did not begin later. It emerged from imperfection at the dawn of time. The universe did not receive rotation as a gift. It unfolded from a state where slight imbalance made motion unavoidable. And as we continue drifting through this origin story, we will look even more closely at how those early asymmetries shaped not only galaxies, but the arrow of time itself, how the first tiny break in perfection set everything, including you, into motion that has never truly stopped. As symmetry continued to fracture in those first fractions of a second, the universe did not become chaotic. It became structured. The separation of forces allowed interactions to specialize. Gravity began sculpting large-scale geometry. The strong nuclear force bound quarks into protons and neutrons. The weak force enabled subtle particle transformations. Electromagnetism would later govern atoms and light. Each force emerging from unity introduced new ways for matter and energy to behave differently in different directions. And difference is the quiet origin of motion. Imagine again a perfectly symmetrical sphere of energy, identical in every direction. In such a state, no direction is preferred. No gradient exists. Without a gradient, nothing flows. Without flow, nothing turns. But once even the slightest asymmetry appears, a region denser by 1 part in 100,000, a particle favored 1 time in a billion gradients form. Gravity pulls slightly more in one place than another. Fields settle into non-uniform configurations. Tiny drifts become currents. Currents become rotations. The cosmic microwave background preserves the memory of those early gradients. When we map its temperature variations across the sky, we see that faint patchwork pattern, warmer and cooler by mere millionths of a degree. Those small differences correspond to density variations in the primordial plasma. Regions slightly denser would later collapse into clusters of galaxies. Regions slightly less dense would expand into cosmic voids. What is remarkable is not that structure formed, but that it formed so quickly. Within a few 100 million years, fully rotating galaxies already existed. The timescale tells us that the seeds of angular momentum were present from the start. Some researchers have explored whether the large-scale alignment, sometimes called the axis of evil, hints at an even deeper feature, that the universe may have possessed a subtle global orientation. Even if this alignment ultimately proves to be statistical coincidence, the mere possibility illustrates something profound. The cosmos does not appear perfectly isotropic at every scale. Small deviations from perfect symmetry are everywhere. and these deviations cascade upward through cosmic history. Let us return briefly to the concept of inflation. During that fleeting expansion, quantum fluctuations were stretched to macroscopic size. Quantum fields at microscopic scales are restless. They fluctuate even in vacuum. These fluctuations are not optional. They arise from the uncertainty principle itself. When inflation magnified them, it effectively froze those fluctuations into the large-scale fabric of space. A tiny ripple became a galaxy cluster. A slight overdensity became a rotating spiral. If any of those primordial fluctuations included angular momentum, and quantum fields naturally include fluctuations in phase and orientation, then that angular momentum would also have been stretched beyond microscopic scale. Another potential fossil of this era lies in primordial gravitational waves. If inflation generated gravitational waves with rotational components, they would imprint curling patterns in the polarization of ancient light. These so-called B-mode patterns resemble tiny swirls across the sky. Detecting them cleanly is extraordinarily difficult, but the concept itself is elegant. Light, traveling for 13.8 billion years, may carry within its polarization the record of the universe's first subtle twist. Not a dramatic spin like a spinning top, but a whisper of rotation embedded in space-time itself. As matter cooled and combined into hydrogen and helium, gravity slowly amplified density variations. Clouds formed. Those clouds did not collapse straight inward. Even a slight imbalance in momentum caused them to rotate as they contracted. And because angular momentum is conserved, contraction increased rotational speed. This is the same principle you see in a figure skater pulling in her arms. When the skater extends her arms, she spins slowly. When she draws them inward, her rotation speeds up. No new force is required. The rotation intensifies simply because the distribution of mass changes while angular momentum remains constant. The early universe behaved the same way. Vast clouds spanning thousands of light years gradually condensed. As they shrank, their inherited angular momentum became more noticeable. Disks formed. Stars ignited at their centers. Around those stars, additional rotating disks formed, giving rise to planets. At every level, rotation was not inserted. It was revealed. Contraction made visible what was already present in faint form. This is why spiral galaxies are so common. Their elegant arms are not accidents. They are natural outcomes of gravitational collapse acting on rotating matter. When astronomers surveyed roughly 15,000 spiral galaxies and examined their handedness, whether their arms curve clockwise or counterclockwise, they found hints of imbalance. The effect remains under discussion, but even a slight statistical preference would reinforce the idea that the cosmos inherited a directional bias from its earliest conditions. What matters most is not whether the universe rotates globally like a rigid body. Observations suggest it does not spin in that simple sense. Rather, what may have existed is a subtle initial distribution of angular momentum that seeded structure everywhere. The total angular momentum across the cosmos remains conserved, but locally it manifests in stars, planets, galaxies, and even black holes. Black holes themselves preserve angular momentum with extraordinary intensity. When massive stars collapse, their cores shrink from thousands of kilometers to perhaps 20 kilometers across. That collapse multiplies their rotational speed dramatically. Some neutron stars rotate hundreds of times per second. Again, nothing external adds that spin. It is the amplification of inherited motion. Broken symmetry allowed these processes to unfold. The separation of forces created complexity. The excess of one matter particle per billion created substance. The Higgs field endowed particles with mass. Inflation stretched quantum fluctuations into structure. Each step introduced slight unevenness. And from unevenness, motion flowed naturally. Time itself depends on this asymmetry. If the universe were perfectly balanced, entropy would not increase. No arrow of time would emerge. But because the early universe began in a low entropy, slightly uneven state, processes unfold directionally. Stars burn fuel. Galaxies merge. Structures evolve. And all the while, angular momentum is passed along like a conserved inheritance. So when you look at a spinning planet or a swirling galaxy, you are not witnessing a late-stage development. You are seeing a continuation of conditions present within the first trillionth of a second. Rotation was never added later to a still universe. It was carried forward from the beginning, amplified by collapse, preserved by conservation, and made visible by broken symmetry. And as we move deeper into this story, we will connect these early asymmetries not only to galaxies and stars, but to the very reason there is structure at all, why anything exists instead of a perfectly smooth sea of radiation, and how that one extra particle in a billion shaped the destiny of motion across 13.8 billion years. Now let us linger with that one extra particle in a billion, because in its quiet imbalance lies the reason rotation did not cancel itself away. In the first microseconds, matter and antimatter were created together, mirror twins born from energy. If perfect symmetry had governed their behavior, every particle would have found its opposite and vanished into light. The universe would have become an ocean of radiation, expanding and cooling without ever forming atoms. No clouds to collapse, no disks to spin, no stars to ignite. But the symmetry was not perfect. For roughly every billion pairs, there was one additional particle of matter. When annihilation occurred, that tiny surplus survived. From that surplus came hydrogen and helium. From those simple elements came stars. From stars came heavier elements. From those elements came planets, oceans, and the molecules that one day learned to contemplate their origin. This slight preference is tied to what physicists call CP violation. Under certain conditions, the laws of physics treat matter and antimatter differently. The difference is subtle, measurable only in delicate particle experiments, yet cosmically decisive. It means that nature does not maintain perfect mirror balance. There is a bias, a directionality embedded in fundamental interactions. And directionality is closely related to rotation. If the laws governing particles distinguish between left and right, then symmetry is already broken at the deepest level. Motion can acquire handedness. Spin can prefer orientation. Cancellation becomes incomplete. In a perfectly symmetrical cosmos, Every rotational tendency might be matched by an equal and opposite counterpart. But once imbalance appears, even slightly, conservation laws preserve whatever net angular momentum remains. As the universe expanded and cooled, that tiny bias became magnified through gravitational amplification. Regions with slight excess density did not collapse uniformly. They contracted while preserving any initial twist. Over time, small eddies became coherent rotations. Think of stirring cream into coffee. At first, you may barely notice the swirl, but as the liquid moves, the rotation spreads, shaping patterns across the cup. The early universe was not stirred by an external spoon, but by its own internal fluctuations. Quantum variations provided the tiniest initial motions. Inflation stretched those motions across cosmic distances. Gravity then sculpted them into structure. The process was self-contained. No external torque was required. Angular momentum did not appear from outside. It was conserved from within. As stars formed within rotating clouds, they inherited angular momentum from their parent regions. When those stars exhausted their fuel and collapsed, their cores shrank dramatically. Conservation demanded that as radius decreased, rotational speed increased. A star rotating once every several days could leave behind a neutron star rotating hundreds of times per second. This is not an exotic addition to physics. It is the same rule governing a spinning skater. The difference is scale. From meters to kilometers to light years, the principle is unchanged. Even the distribution of galaxies across cosmic filaments reflects early asymmetries. The large-scale structure of the universe resembles a vast web, with clusters connected by elongated strands of matter and enormous voids in between. Those filaments trace back to the original 1 part in 100,000 density variations in the cosmic microwave background. Where density was slightly higher, gravity gathered material. Where slightly lower, expansion dominated. The web-like pattern that emerged is a fossil of broken symmetry. And within those filaments, galaxies rotate. The age of the universe, about 13.8 billion years, is long enough for many transformations, yet throughout all those epochs the total angular momentum has remained conserved. It has shifted from diffuse plasma to rotating stars, from stars to black holes, from galaxies merging into new systems. But nowhere in that entire span does motion disappear. Changes form. It redistributes. It intensifies in some regions and diffuses in others. Yet the accounting remains balanced. When the Higgs field acquired its non-zero value around 10 to the minus 12 seconds, particles gained mass and thus inertia. Inertia allows rotation to persist. Without mass, particles traveling at light speed cannot form stable rotating structures. With mass, matter can orbit, cluster, and resist changes in motion. That transition was essential. It anchored rotation into material form. It is worth noticing how delicate all of this is. If the density fluctuations in the early universe had been much larger than 1 part in 100,000, matter would have collapsed too quickly into black holes. If they had been much smaller, gravity would never have overcome expansion to form galaxies. If matter and antimatter had been exactly equal, no atoms would exist. If the Higgs field had settled differently, particles might not have acquired mass at all. Each asymmetry sits within a narrow range that allows structure and motion to unfold over billions of years. And so we arrive at a quiet realization. Rotation is not an isolated phenomenon that began when galaxies formed. It is woven into the chain of asymmetries that began during the earliest instance of cosmic history. From the Planck era through inflation, through symmetry breaking, through baryon asymmetry, through the emergence of mass, each stage preserved and amplified directional differences. When we observe spiral galaxies today, or measure the spin of pulsars, or detect the angular momentum of black holes, we are not seeing newly invented motion. We are seeing inheritance, a continuity extending back to the first trillionth of a second. The universe did not pause in stillness and then begin turning later. It unfolded from a slightly uneven beginning where motion was already embedded in its quantum fabric. This is why rotation feels so universal. From electrons with intrinsic spin to planets rotating on their axes, from galaxies turning over hundreds of millions of years to clusters drifting through cosmic filaments, motion is everywhere. Not imposed, but conserved. Not added, but inherited. In the final stretch of this part of our journey, we will gather these threads together, the early quantum fluctuations, the broken symmetries, the one extra particle per billion, and see how they converge into a single quiet truth: that existence itself depends on imperfection, and that the first cosmic turn was not a dramatic event in time, but the natural consequence of a universe that was never perfectly balanced. As we gather all these threads together, the story becomes softer, yet deeper. In the first 10 to the minus 43 seconds during the Planck era, physics as we know it dissolves into uncertainty. Gravity and quantum mechanics are thought to merge there, and our equations can only gesture toward what occurred. But even in that unknowable beginning, there is no compelling reason to imagine absolute stillness. Quantum fields fluctuate by necessity. Perfect uniformity is unstable at that scale. If fluctuation is unavoidable, then slight directional differences are unavoidable. And once directional difference exists, conservation laws ensure that motion persists. From that earliest flicker, inflation stretched space faster than light could travel, smoothing the cosmos yet freezing microscopic variations into macroscopic structure. Those variations were tiny, 1 part in 100,000 in temperature across the young universe, yet they were enough. They formed gravitational wells and peaks. Matter streamed toward those wells. As it streamed, it did not fall straight inward in pristine symmetry. Even the faintest lateral component in velocity created a curve. A curve became a swirl. A swirl became rotation. When symmetry broke and the 4 fundamental forces separated, new behaviors became possible. Gravity began shaping cosmic architecture. The strong force bound atomic nuclei. The weak force allowed particle transformations that favored matter slightly over antimatter. The electromagnetic force would later orchestrate atoms and light. Each separation introduced complexity, and complexity amplifies asymmetry. The baryon asymmetry, that single extra matter particle per billion, ensured that annihilation did not erase substance entirely. Without that imbalance, There would be no rotating gas clouds, no stellar disks, no galaxies turning through darkness. The Higgs field settling into a non-zero value around 10 to the minus 12 seconds granted mass to particles. Mass created inertia. Inertia allowed angular momentum to manifest in stable systems. Every stage of early cosmic history reinforced the persistence of motion. It is tempting to imagine a moment when someone or something set the universe spinning. But physics offers a quieter answer. There was no external push, no cosmic hand imparting torque. Instead, slight imperfections in an expanding quantum field carried tiny angular imbalances forward. Those imbalances were preserved by conservation laws. As the universe cooled and structure emerged, contraction amplified those imbalances naturally. The figure skater analogy returns here not as poetry, but as physics. When mass pulls inward, rotation speeds up. Nothing mystical, only conservation. The evidence that rotation is primordial rather than added later appears in how early galaxies formed. Even systems observed less than a billion years after the Big Bang already show organized motion. They did not require billions of years to learn to spin. They condensed from rotating gas. That gas condensed from rotating density fields. Those fields arose from stretched quantum fluctuations. And those fluctuations existed within the first fractions of a second. Some studies of spiral galaxy handedness suggest a subtle statistical bias in rotational direction. Whether that effect ultimately proves fundamental or statistical noise, the mere plausibility underscores how deeply motion is embedded in cosmic structure. At every scale we observe, from atomic spin to galactic rotation, angular momentum appears not as an exception but as a rule. The cosmic microwave background still surrounds us, a faint whisper from 380,000 years after the Big Bang. Its anisotropies show the seeds of structure. Its polarization patterns may even carry the faint curling imprint of primordial gravitational waves. If B-mode polarization truly encodes those early ripples, then the universe has left behind a fossil record of its first motions, etched into ancient light. Over 13.8 billion years, stars have been born and extinguished, galaxies have collided and merged, black holes have grown and consumed. Through all of it, angular momentum has never been destroyed. It has shifted form. A collapsing star's spin becomes a pulsar's rapid rotation. Merging galaxies redistribute their combined angular momentum into new stellar orbits. Even when matter falls into a black hole, its angular momentum shapes the geometry of spacetime around it. Motion is conserved not only in matter, but in curvature itself. This continuity leads to a simple but profound realization. Rotation was not added to a once-still cosmos. It was inherited from a universe that began slightly imperfect. Symmetry broke. Forces separated. Matter gained a fractional advantage. Fields settled into uneven states. From those uneven beginnings, motion became inevitable. Perfect symmetry would have produced nothing. Imperfection produced everything. And here is the most calming part of this story. The same laws that governed those first fractions of a second still govern the present moment. The spin of Earth beneath you is part of the same conservation chain. the orbit of the Moon, the revolution of the Milky Way every 230 million years, the intrinsic spin of electrons inside your atoms, all are chapters of a single continuous inheritance. Nothing had to restart rotation later in cosmic history. Nothing intervened to add it. The universe unfolded from a state where slight asymmetry made motion unavoidable. Every swirl of a galaxy is an echo of that early imbalance. Every turning planet is a descendant of primordial fluctuation. So when we ask who set the universe spinning, the answer is gentler than myth. No one set it spinning. It was born with slight unevenness, and from that unevenness, motion naturally followed. Rotation is not a feature imposed on existence. It is the expression of a universe that was never perfectly balanced. And as you rest within this immense inheritance, remember that the atoms within you still carry that ancient motion forward. You are part of a turning that began before light, before stars, before time felt measurable. The first cosmic turn was not a dramatic twist in empty space. It was the quiet consequence of broken symmetry, preserved across 13.8 billion years. If you're still here with the universe turning softly around you, type 2 in the comments. Right now, beneath your feet, the Earth is turning at about 1,037 miles per hour at the equator. You do not feel it. You do not lean into it. You do not brace against it. Yet every second, you are carried eastward at a speed faster than most aircraft ever fly. One full rotation takes 23 hours, 56 minutes, and 4 seconds. That is a sidereal day measured against distant stars rather than the sun. It is the quiet mechanical heartbeat of our world. This rotation is not decorative. It is necessary. Without it, Earth would not be the living planet, Because the planet turns, sunlight is shared. Day transitions into night. Heat is distributed rather than hoarded. Energy flows across continents and oceans in a slow, reliable rhythm. Imagine gently a world that does not rotate. One hemisphere would face the sun continuously. That side would bake under relentless radiation. Oceans would evaporate. Atmospheres would expand and thin. The opposite side would freeze in darkness, its gases condensing, its water locked in endless ice. Between those extremes, violent winds would rage as hot air rushed toward cold, trying to balance a planet that refused to turn. But Earth does turn, and because it turns, the boundary between light and dark moves constantly. No place is condemned to permanent fire or permanent frost. The distribution of energy becomes dynamic instead of static. Motion prevents extremes. The turning also shapes the air itself. As warm air rises near the equator and moves toward the poles, the planet's rotation bends its path. This deflection is called the Coriolis effect. In the northern hemisphere, moving air curves to the right. In the southern hemisphere, it curves to the left. From that simple rule emerges the grand architecture of atmospheric circulation. Trade winds, jet streams, spiraling storms. Hurricanes spin because Earth spins. Ocean currents arc across basins because Earth turns beneath them. The great conveyor belts of climate depend on rotation to organize movement into patterns instead of chaos. Without that steady spin, weather would not arrange itself into semi-predictable systems. It would become erratic, extreme, unstable. Rotation also works deeper than wind and cloud. Beneath the crust, Earth's outer core flows. It is composed largely of liquid iron, churning slowly around a solid inner core. This motion, combined with planetary rotation, generates a magnetic dynamo. The result is a magnetic field stretching far into space, wrapping the planet in an invisible shield. That field protects us from the solar wind, a continuous stream of charged particles emitted by the sun. Without magnetic protection, those particles would gradually erode the atmosphere. We have evidence of this on another world. Mars rotates once every 24.6 hours, similar to Earth, but its smaller size allowed its core to cool more quickly. When its internal dynamo faded, its global magnetic field weakened and largely vanished. Over time, the solar wind stripped away much of its atmosphere. What remains is thin, cold, and dry. Earth's rotation, paired with its molten core, keeps our magnetic shield alive. When charged particles collide with that field near the poles, they create auroras, shimmering curtains of light. Beauty is born from protection, and protection is born from motion. Even the length of our day is not fixed. The moon's gravity pulls on Earth's oceans, creating tides. Those tides create friction against the seafloor. That friction very slowly drains rotational energy from the planet. On average, Earth's day grows longer by about 1.7 milliseconds per century. It is an almost imperceptible change, but measurable with atomic clocks. As Earth slows, the moon drifts away at roughly 1.5 inches per year. The two bodies exchange angular momentum in a gradual gravitational conversation. Billions of years ago, a day on Earth lasted perhaps 6 hours. Today it lasts nearly 24. In the distant future, it will be longer still. Yet the moon does more than slow us. It stabilizes Earth's axial tilt. Our planet leans about 23.5 degrees relative to its orbit around the sun. That tilt gives us seasons. Without the moon's steady gravitational influence, simulations suggest Earth's tilt could wobble chaotically over time, swinging between extremes. Such dramatic shifts would produce severe climate instability. Instead, our axial tilt remains relatively stable, allowing life to adapt to predictable seasonal cycles. Rotation, tidal interaction, axial tilt, magnetic dynamo. These are not separate stories. They are interwoven consequences of a spinning world. If you widen your view, you see how different rotational speeds produce different outcomes. Jupiter completes one rotation in about 9 hours and 56 minutes. That rapid spin flattens the planet at its poles and drives intense atmospheric bands. Enormous storms, including the Great Red Spot, are sustained by the energy of that swift rotation. Venus offers a contrasting case. It rotates extremely slowly and in the opposite direction of most planets. One rotation takes about 243 Earth days. Its sluggish, retrograde spin and thick carbon dioxide atmosphere have contributed to a runaway greenhouse effect. Surface temperatures are hot enough to melt lead. This magnetic field is weak compared to Earth's. Mars, with its day only slightly longer than ours, shows how rotation alone is not enough. Without a sustained internal dynamo, its magnetic shield failed. Motion must be coupled with internal heat and fluidity to sustain protection. Across these examples, a theme emerges gently. Rotation is not merely movement. It is structure. It organizes energy, shapes climate, supports magnetic fields, and stabilizes long-term conditions. Life does not arise in stillness. It arises where energy flows are moderated, where extremes are softened, where motion distributes heat and charge. Our planet's rotation is the quiet architect of its habitability. It does not announce itself. It does not shake the ground. It simply continues, steady and ancient, defining day and night, guiding winds, shielding air, pacing the rhythm of life. And as we continue drifting deeper, we will look beyond our solar system to distant worlds where astronomers now search for similar spinning balances, asking whether rotation elsewhere might also cradle the possibility of life. When astronomers search for life beyond our solar system, they do not look only for water. They look for motion. A planet may sit at the right distance from its star, within what is often called the habitable zone, but if it does not rotate in a balanced way, that favorable position may not be enough. Rotation determines how energy is transported across a world's surface, how atmospheres circulate, and whether temperatures remain stable over time. Without circulation, even a planet bathed in gentle starlight could become hostile. The James Webb Space Telescope has begun revealing the atmospheres of distant exoplanets with remarkable sensitivity. On worlds like WASP 39b, a gas giant orbiting close to its star, Webb detected complex atmospheric chemistry and clear evidence of large-scale circulation. Winds redistribute heat from the intensely illuminated side facing the star to the cooler side facing away. Even though WASP 39b is not habitable, its atmosphere demonstrates a principle: motion spreads energy. Without that redistribution, temperature differences would become extreme and destabilizing. On smaller rocky exoplanets, such as TRAPPIST-1e, scientists model how rotation and atmospheric circulation might allow liquid water to persist. Many planets orbiting small red dwarf stars are tidally locked, meaning one side always faces the star, while the other remains in darkness. At first glance, this seems fatal for life. One hemisphere would overheat, the other would freeze. But climate simulations show that if the atmosphere is thick enough and circulation strong enough, heat can still be transported around the planet. Winds driven by rotation can carry warmth into the dark side, softening the extremes. Again, motion becomes the mediator between fire and ice. Rotation does not simply create days and nights, it creates gradients, and gradients are essential for life. Life feeds on differences in temperature, in chemical concentration, in electrical charge. A world without gradients is a world without flow. A world without flow is chemically stagnant. Rotation keeps gradients alive by constantly shifting energy across space. Even on Earth, The delicate balance of climate depends on this redistribution. The equator receives more solar energy than the poles. Because the planet spins, air and water move in great loops, transferring heat poleward. The Hadley cells rise near the equator and descend at subtropical latitudes. Ocean currents carry warm water northward and cold water southward. This continuous circulation keeps the planet within relatively narrow thermal limits. Without rotation shaping these flows, equatorial regions might become unbearably hot, while polar regions deepened into permanent ice. The importance of rotation reaches further inward, down to the molecular foundations of life itself. All living organisms on Earth share a striking feature known as chirality, or handedness. Amino acids, the building blocks of proteins, are almost exclusively left-handed. DNA, the molecule that stores genetic information, forms a right-handed double helix. In laboratory chemistry, left and right-handed molecules can often form in equal amounts. Yet life chose one orientation and maintained it with unwavering consistency. This preference may not be random. In 1969, the Murchison meteorite fell in Australia. When scientists analyzed its contents, they found amino acids with a slight excess of left-handed forms. These molecules were not produced by earthly biology. They formed in space long before our planet existed. That suggests that the bias toward left-handed amino acids may have cosmic origins. At the subatomic level, nature itself displays asymmetry. In 1956, an experiment led by physicist Chien-Shiung Wu demonstrated that the weak nuclear force violates parity symmetry. Certain particles, such as neutrinos, exhibit a consistent left-handedness. They spin in a preferred orientation relative to their direction of motion. The universe, at its most fundamental level, does not treat left and right equally. Light also carries spin. Photons can be polarized in left-handed or right-handed circular orientations. In star-forming regions, light scattering through magnetic fields can become partially polarized. Some researchers propose that such polarized radiation in the early solar system could have selectively destroyed one molecular orientation more than the other, gradually amplifying a small initial imbalance. Over time, that tiny bias may have shaped the chemistry that later blossomed into biology. Here, again, motion is central. Polarization arises from electromagnetic waves oscillating in particular directions. Magnetic fields arise from moving charges. Stellar radiation interacts with rotating dust grains aligned by magnetic fields. The entire chain from cosmic rotation to molecular handedness is built on dynamic processes, not static ones. Life thrives because motion distributes energy and because asymmetry allows structure. A perfectly symmetrical, perfectly still universe would produce no chemistry complex enough to sustain organisms. But a universe filled with rotating stars, spinning planets, flowing atmospheres, and polarized light naturally creates imbalances. And from imbalance comes possibility. When you consider the arc from Earth's 1,000-mile-per-hour spin to the left-handed twist of an amino acid, you begin to see a continuity. The same physical laws that govern planetary rotation govern particle spin. The same conservation of angular momentum that shapes galaxies influences the orientation of molecules. Rotation is not only a large-scale astronomical feature, it is woven into matter itself. Life, then, may be understood as an intricate pattern sustained by motion. Cells rely on gradients across membranes. Enzymes twist and fold in precise orientations. DNA coils and uncoils as it is read and copied. Even at the cellular level, tiny molecular motors rotate, transporting cargo within living tissue. Stillness at any of these levels would mean collapse. The quiet architect of habitability is not simply distance from a star. It is not only the presence of water. It is the ongoing distribution of energy through motion. Rotation smooths extremes, sustains magnetic shields, stabilizes climates, and perhaps even biases chemistry toward life-friendly structures. As we continue, we will look more closely at how this subtle choreography of motion connects the spin of worlds to the very rhythm of living systems, tracing the thread from planetary dynamics down to the deepest physical asymmetries that make existence possible. If you narrow your focus from planets to oceans, and from oceans to cells, the same principle continues quietly. Life depends on the steady distribution of energy. On Earth, rotation prevents stagnation not only in the atmosphere, but in the seas. As the planet turns, winds driven by temperature gradients sweep across the surface, dragging the upper layers of the ocean with them. These moving waters form gyres, vast circular currents shaped by the Coriolis effect. Warm water travels toward cooler regions. Cold water sinks and eventually rises again in distant places. Nutrients cycle upward from the deep, feeding microscopic plankton that form the base of marine food webs. Without this rotation-shaped circulation, the oceans would stratify more rigidly. Surface waters might warm and remain nutrient-poor, while the deep would grow isolated and chemically stagnant. Instead, motion knits the layers together. Rotation also influences the mixing of the atmosphere with the ocean. Coastal upwelling zones, created by wind patterns deflected by Earth's spin, bring nutrient-rich waters to the surface. These regions become some of the most biologically productive places on the planet. Fisheries flourish there. Entire ecosystems rely on a subtle bending of moving air caused by a spinning globe. It is easy to overlook how much of life's abundance rests on this invisible deflection. Even the stability of long-term climate is linked to rotation. Earth's axial tilt, held relatively steady by the gravitational partnership with the Moon, ensures that seasonal changes are moderate rather than catastrophic. If the tilt swung wildly over millions of years, ice ages and heat waves would intensify beyond the tolerance of complex organisms. The Moon's presence dampens these oscillations, acting like a stabilizing weight on a spinning top. Because the top spins, it resists falling. Because Earth spins and carries its lunar companion, its orientation remains predictable enough for forests, coral reefs, and migrating animals to adapt across generations. Consider again the alternative. A non-rotating Earth would not only suffer extreme heating on one side and freezing on the other. Its magnetic dynamo would weaken without the same organized internal motion. Without a magnetic field, the atmosphere would gradually thin under the persistent assault of charged solar particles. Ultraviolet radiation would penetrate more deeply. Surface water would slowly be lost to space. Over vast timescales, the ingredients for life would be stripped away. Rotation is not merely about comfort. It is about retention. Keeps air bound to the planet and shields delicate chemistry from disruption. Now widen the perspective to the entire biosphere. Nearly every organism on Earth is synchronized to the cycle of light and dark. Circadian rhythms, internal biological clocks, evolved in response to the planet's 24-hour cadence. Plants open and close their leaves according to daylight. Animals sleep and wake in patterns aligned with rotation. Even single-celled organisms exhibit gene expression cycles tuned to this planetary period. If Earth's rotation were drastically slower or faster, evolutionary pathways would diverge. Longer days would mean longer heating and cooling phases. Shorter days would compress metabolic cycles. The tempo of life is set by spin. The deeper you look into living cells, the more rotation appears again. Proteins fold into precise three-dimensional shapes, often twisting into helices. DNA coils in a right-handed spiral, its structure stabilized by the consistent chirality of its components. Enzymes bind substrates in orientations that depend on molecular handedness. If right-handed amino acids dominated instead of left-handed ones, the entire architecture of biology would differ. Perhaps it would not function at all in the same way. The Murchison meteorite's slight excess of left-handed amino acids suggests that this preference predates Earth. It hints that the building blocks of life arrived already biased. That bias may trace back to polarized radiation in star-forming regions or to deeper asymmetries in particle physics. Neutrinos exhibiting left-handedness remind us that even at the level of fundamental forces, symmetry is imperfect. The weak interaction distinguishes left from right. The universe contains directionality woven into its laws. This connection between cosmic scale rotation and microscopic chirality may seem abstract, but it rests on continuity. Magnetic fields arise from moving charges. Polarized light emerges from electromagnetic waves carrying angular momentum. Molecules interact differently with left or right polarized photons. In this way, stellar rotation influencing magnetic alignment in interstellar clouds could cascade down to subtle chemical preferences. The path from spinning galaxies to spiraling DNA is long, but it is not broken. Rotation distributes energy and also selects structure, prevents stagnation and promotes gradients. Gradients drive chemistry. Chemistry, under the right conditions, becomes biology. A world without rotation would be chemically simpler, climatically harsher, magnetically weaker, and biologically poorer. Motion makes complexity sustainable. Think again of Jupiter, spinning rapidly and generating powerful magnetic fields. Though it is not habitable in the way Earth is, its rotation shapes a dynamic system of storms and radiation belts. Think of Venus, turning slowly and lacking a strong magnetic shield, its surface locked in oppressive heat. Think of Mars, rotating at a comfortable pace but missing the internal motion to sustain protection. Each example underscores that rotation must be paired with internal energy and balanced conditions. It is not enough to spin. The spin must integrate with structure. Earth achieved that balance. Its rotation is fast enough to create meaningful Coriolis forces and efficient heat distribution, yet slow enough to avoid violent atmospheric extremes. Its molten core remains active, sustaining a magnetic field. Its moon moderates axial tilt. Its oceans circulate under the influence of wind and spin. Its biosphere adapted to the rhythm. Life thrives because motion distributes energy. Rotation is the quiet architect of habitability. It does not announce itself in thunder or flame. It simply continues, turning the planet beneath you, guiding winds, sustaining tides, shaping the very molecules from which you are built. If you're still drifting with this planetary rhythm, type 3 in the comments. There is another layer to this quiet architecture, one that unfolds over immense stretches of time. Earth's rotation is not perfectly constant. It breathes, subtly, through interactions with its surroundings. The moon's gravity raises tidal bulges in the oceans, and because Earth spins faster than the moon orbits, those bulges are carried slightly ahead of the line connecting the two bodies. Gravity pulls backward on the bulges, gently breaking Earth's rotation. In response, angular momentum is transferred to the moon, pushing it farther away at roughly 1.5 inches per year. Each century, the length of our day increases by about 1.7 milliseconds. It is an almost imperceptible slowing, yet over billions of years it has transformed a once 6-hour day into the calm 24-hour rhythm we now inhabit. Life evolved within this gradually lengthening cycle, adapting to a tempo that was never fixed but always smooth. This steady breaking has consequences beyond timekeeping. Slower rotation reduces the equatorial bulge of the planet and slightly alters global circulation patterns. Yet because the change is so gradual, ecosystems adjust. The stability of this transition matters. Sudden shifts in rotation would be catastrophic. Gradual change allows life to track the moving target of planetary conditions. Rotation, in this sense, is not only an architect but a patient sculptor. The interplay between rotation and gravity extends to axial tilt as well. Earth leans at about 23.5 degrees, creating seasons that migrate gently across the globe each year. Without the moon's stabilizing torque, gravitational tugs from other planets could cause chaotic variations in tilt over millions of years. Large swings in obliquity would mean extreme climate oscillations, alternately scorching and freezing entire regions. Instead, the moon acts as a stabilizing partner, smoothing these variations and maintaining a relatively narrow range of tilt. The combination of spin and lunar companionship keeps seasonal cycles within bounds that life can tolerate. When scientists examine exoplanets, they increasingly ask whether similar stabilizing mechanisms exist elsewhere. A rocky world in the habitable zone may still fail to support life if its rotation is too slow, too fast, or too erratic. A tidally locked planet orbiting close to a small star might show the same face to its sun at all times. On such a world, the day side would receive constant radiation while the night side would remain dark. Yet even here, rotation relative to the star is not the only variable. Atmospheric circulation, driven by internal heating and planetary spin, can carry warmth into darkness. If winds are strong and oceans deep, the boundary between hot and cold may soften, allowing temperate regions to exist. Climate models suggest that on certain tidally locked planets, a ring of habitability could form around the twilight zone where day meets night. Once again, motion distributes energy and prevents collapse into extremes. The theme repeats across scales. Inside Earth's core, the slow convection of liquid iron generates electric currents. Those currents produce a magnetic field that extends far into space, deflecting charged particles from the sun. Without this field, the upper atmosphere would be gradually eroded. Mars offers a quiet warning. Though it rotates once every 24.6 hours, its smaller size allowed its internal heat to dissipate more quickly. When its dynamo shut down, its magnetic shield weakened. Over time, solar winds stripped away much of its atmosphere. Surface water evaporated or froze. The planet that may once have had rivers and lakes became a cold desert. Rotation alone was not enough. Sustained internal motion was required. On Earth, that internal and external motion work together. The spinning mantle and core, the orbiting moon, the circulating oceans, the flowing air, the migrating seasons, and the daily alternation of light and dark form a single integrated system. Life exists within this moving framework. Photosynthesis depends on sunlight cycling in and out. Predators and prey align their behaviors with diurnal patterns. Reproduction, migration, flowering, and hibernation are all timed to rotational cues. Even human technology is calibrated to planetary spin. Our clocks, our calendars, our entire sense of time are anchored to this turning. At the molecular level, the story deepens. DNA's right-handed helix is not merely a structural curiosity. Its shape influences how it replicates and how proteins bind to it. Amino acids, almost exclusively left-handed in terrestrial life, assemble into proteins whose folding patterns depend on that orientation. If you were to mirror all biological molecules, they would no longer interact correctly with one another. The entire chemistry of life would fail to recognize itself. That consistent handedness is a frozen imprint of ancient asymmetry. The origin of this asymmetry may trace back to polarized radiation in early star-forming regions or to deeper physical laws that favor one orientation over another. The weak nuclear force distinguishes left from right in subtle but measurable ways. Neutrinos, for example, are observed only in left-handed configurations relative to their motion. The universe, even at its most fundamental level, is not perfectly symmetrical. That slight bias, amplified over cosmic time, may have nudged chemistry toward a single consistent handedness. The chain from particle spin to biological chirality is long, yet it is continuous. Angular momentum and asymmetry ripple from the smallest scales to the largest. Rotation distributes energy. Asymmetry allows structure. Together, they create the conditions under which complexity can grow. A static universe, perfectly balanced and perfectly symmetrical, would offer no gradients to exploit, no flows to harness, no biases to build upon. But our universe is dynamic and slightly uneven. Planets spin, stars rotate, galaxies swirl, Particles possess intrinsic angular momentum. From these motions and imbalances arise magnetic fields, climates, chemical networks, and ultimately organisms capable of reflection. Earth's rotation, then, is not an isolated fact. It is part of a broader cosmic inheritance. The same conservation of angular momentum that shaped the early solar system continues to operate now, gently slowing the day, guiding tides, and preserving stability. Life thrives because motion never fully ceases. Energy is constantly redistributed, not allowed to pool into sterile extremes. The quiet architect of habitability is not only distance from a star or the presence of water. It is the persistent turning that keeps everything in balance, from the atmosphere above you to the molecules within you. As we move into the final stretch of this exploration, we will gather these threads together and consider how this persistent motion, from planetary spin to molecular twist, forms a single unbroken story about why living worlds are not accidents of stillness, but expressions of a universe in motion. If you step back now and hold the entire picture in your mind, a quiet pattern becomes visible. Rotation is not a background detail. It is a continuous thread running from the scale of planets to the scale of particles. Earth turns at 1,037 miles per hour at the equator. It completes a sidereal rotation in 23 hours, 56 minutes, and 4 seconds. That steady turning distributes sunlight, shapes winds, stirs oceans, powers a magnetic dynamo, stabilizes climate, and sets the biological tempo of nearly every organism alive. It is not dramatic. It is dependable, and that dependability is what allows life to persist. The moon slowly breaks that spin by about 1.7 milliseconds per century, drifting away by roughly 1.5 inches each year. Yet even this slowing is part of the same story. Angular momentum is not destroyed. It is exchanged. The Earth-Moon system adjusts itself in a slow gravitational dialogue. Stability is preserved not through rigidity, but through motion shared and redistributed. Look outward again to other worlds. Jupiter spins in just under 10 hours, its rapid rotation sculpting banded clouds and sustaining colossal storms. Venus rotates once every 243 Earth days, slowly and in retrograde, its surface locked beneath crushing heat and a weak magnetic presence. Mars turns at a familiar pace, yet without a sustained internal dynamo, its atmosphere thinned and its surface dried. These comparisons reveal something subtle. Rotation must exist in harmony with mass, composition, and internal heat. Spin alone does not guarantee life, but without spin, life as we understand it struggles to emerge at all. Beyond our solar system, astronomers observe exoplanets where atmospheric circulation redistributes heat across hemispheres. On worlds that may be tidally locked, winds could carry warmth from permanent day into permanent night, softening extremes. The lesson remains the same. Motion prevents stagnation. Energy must flow. Temperature differences must be moderated rather than amplified beyond survival. Now travel inward again, past oceans and air, past cells and membranes, into molecular structure. Life on Earth relies on chirality. Amino acids are overwhelmingly left-handed. DNA forms a right-handed double helix. This handedness is not arbitrary decoration. It determines how molecules fit together, how enzymes recognize substrates, how genetic information is stored and copied. If life's molecules were mirrored, the entire biochemical system would fail to function as it does. The presence of a left-handed excess in the Murchison meteorite suggests that this bias predates Earth. It implies that the seeds of biological asymmetry were already present in space. That bias may have been influenced by polarized radiation in star-forming clouds, where light itself carries angular momentum. Photons can possess left or right-handed polarization, interacting differently with chiral molecules. Over long timescales, even a tiny imbalance can be amplified. Deeper still, the weak nuclear force reveals a fundamental asymmetry in nature. In the 1956 experiment led by Qian-Xiong Wu, it became clear that certain particle interactions do not treat left and right equally. Neutrinos exhibit consistent left-handedness. Parity symmetry is violated at the subatomic level. The universe contains direction built into its laws. The same cosmos that spins galaxies also distinguishes between orientations of spin in its most basic interactions. It is tempting to separate these domains: planetary rotation, atmospheric circulation, magnetic fields, molecular chirality, particle physics. But they are expressions of the same principle. Angular momentum is conserved. Motion is inherited. Asymmetry allows structure to emerge. Rotation distributes energy so that gradients exist without becoming catastrophic. Life thrives because energy does not remain trapped. On Earth, the equator receives more sunlight than the poles. Rotation organizes air and water into patterns that transport that excess heat outward. Within cells, chemical gradients across membranes power metabolism. Within ecosystems, seasonal cycles driven by axial tilt coordinate growth and dormancy. At every scale, flow replaces stillness. Imagine a universe without rotation. No spinning planets. No circulating atmospheres. No magnetic dynamos. No polarized light. No intrinsic particle spin. Energy would settle evenly. Temperatures would equalize without circulation. Chemical reactions would lack directional bias. Structure would struggle to persist. A perfectly still universe would be a quiet but sterile one. Instead, our universe is restless. Not violently so at every moment, but fundamentally dynamic. Galaxies rotate. Stars spin. Planets turn. Particles possess intrinsic angular momentum. From this pervasive motion arises everything complex. Rotation is the quiet architect of habitability because it prevents energy from collapsing into unusable extremes. It spreads warmth, sustains shields, stabilizes orientation, and perhaps even nudges chemistry toward life-friendly configurations. As you lie still, feeling nothing of Earth's 1,000-mile-per-hour motion, remember that this invisibility is itself a gift. Uniform motion feels like rest. The planet carries you smoothly, distributing sunlight and sustaining air while you remain unaware of the speed. Your body's cells operate within rhythms set by that spin. Your DNA coils in a direction shaped by ancient asymmetry. The magnetic field above you deflects charged particles because molten iron still circulates deep below. Life does not exist in spite of motion. It exists because of it. From the turning of the earth to the handedness of molecules, motion shapes possibility. Rotation is not noise in the background of existence. It is the structure that makes living worlds stable enough to endure and dynamic enough to evolve. If you're still drifting with this planetary rhythm, type 3 in the comments. In 1915, Albert Einstein published his general theory of relativity, and with it, the universe changed forever. Gravity was no longer a simple pull between masses as Isaac Newton had described. Instead, Einstein revealed something quieter and far more profound. Mass and energy bend space-time itself. Space is not empty. Time is not rigid. They form a single fabric, and that fabric can curve, stretch, and twist. If a massive object sits within it, space-time curves. If that object spins, space-time does not merely curve, it swirls. This swirling has a name: frame dragging. Imagine space-time as a vast, invisible ocean. A still planet resting in it would make a gentle depression. But a spinning planet would stir the water. The faster it spins, the more it drags the surrounding fabric along with it. Even time becomes slightly twisted in the direction of rotation. For decades, this effect remained theoretical. It was subtle beyond imagination. But in 2004, NASA launched Gravity Probe B, a satellite carrying 4 of the most precise gyroscopes ever built. Orbiting about 400 miles above Earth, it measured how much our planet's rotation twisted space-time. After careful analysis, scientists confirmed Einstein's prediction. Earth drags space-time by about 0.000011 degrees per year. That number sounds almost meaningless. Yet its agreement with Einstein's equations was astonishing. Even our calm, blue planet, rotating once every 23 hours, 56 minutes, and 4 seconds, is bending time around it. The motion that gives us sunrise and sunset also gently distorts the geometry of reality. We do not feel it, but it is happening beneath every second of our lives. Now imagine something far more extreme. When a massive star exhausts its nuclear fuel, gravity wins. The core collapses inward with unimaginable force. Protons and electrons merge into neutrons, and the star becomes a neutron star, an object only about 12 miles across, yet heavier than our sun. As it shrinks, it spins faster, conserving angular momentum. Like a figure skater pulling in her arms, collapse increases rotation. Some neutron stars rotate up to 700 times per second. 700 full spins in one single second. Astronomers call many of them pulsars because beams of radiation sweep outward from their magnetic poles. Each rotation sends a pulse across space, so precise that some pulsars rival atomic clocks. Near such an object, gravity is so intense that time itself slows measurably. This is gravitational time dilation. According to relativity, the stronger the gravity or the faster the motion, the slower time passes relative to distant observers. If you could stand near a rapidly spinning neutron star, your clock would tick more slowly than one on Earth. Minutes for you might correspond to hours elsewhere. The faster the spin, the deeper the distortion. Space-time is not merely curved, it is wound tight. Light itself bends around these objects, forced into arcs by gravity. The universe becomes elastic under rotation. This effect reaches its most dramatic form in rotating black holes. In 1963, mathematician Roy Kerr found a solution to Einstein's equations describing a spinning black hole. Unlike a simple, non-rotating black hole, a Kerr black hole does more than pull inward. It twists spacetime around its axis. Outside its boundary lies a region called the ergosphere. Within this region, spacetime is dragged so violently that nothing can remain stationary. Not particles, not light. Everything must rotate with the black hole. It is as if space itself becomes a whirlpool. At the edge sits the event horizon, the boundary beyond which nothing can return. Inside that horizon, escape is impossible. But even outside it, rotation dominates. Close enough to a fast-spinning black hole, the dragging of spacetime approaches the speed of light. Time for a nearby observer would pass dramatically slower compared to someone far away. In 2019, the Event Horizon Telescope released humanity's first image of a black hole, M87 star, a supermassive black hole in a distant galaxy. In 2022, it revealed Sagittarius A star, the black hole at the center of our Milky Way. The glowing rings in those images are not the black holes themselves. They are light from matter spiraling around them, bent and delayed by warped spacetime. Those images were more than photographs. They were visual proof that rotation and gravity together sculpt time. The bright crescent shape shows asymmetry caused by rapid motion. Even light cannot escape distortion near a spinning giant. And yet, this bending of time is not confined to distant galaxies. It touches your daily life. The global positioning system relies on satellites orbiting Earth at about 8,700 miles per hour, roughly 12,500 miles above the surface. Because they are moving faster and experiencing weaker gravity than clocks on Earth, their onboard atomic clocks tick differently. Combined effects of motion and gravity cause them to gain about 38 microseconds per day compared to Earth-based clocks. 38 millionths of a second may sound trivial, but without correction, GPS navigation would drift by miles within a single day. Engineers must constantly adjust for relativity. Your phone works because Einstein was right, so rotation bends time. From Earth's gentle spin to neutron stars' furious revolutions, from orbiting satellites to supermassive black holes, motion reshapes duration itself. Time is not universal. It flows differently depending on how deeply spacetime is stirred. The seconds you experience are defined by Earth's rotation and gravity. Elsewhere, they stretch and compress. The universe does not share one clock, keeps many, each tuned to local motion. Take a slow breath. Even now, as you lie still, you are carried by a rotating planet that slightly twists the geometry around you. Your sense of now is tied to that motion. If spin can bend time, then time is not a backdrop. It is born from movement, and as we drift further into this turning universe, we begin to see that spin does not only shape the present. It may also shape the fate of everything that turns. If rotation can bend time in extreme places, it also quietly shapes the long future of quieter worlds. Spin is not permanent in its original form. It evolves. It redistributes. Even Earth's steady turning is gradually slowing. The moon's gravity raises tides in our oceans, and as those tides move across the surface, they create friction. That friction transfers angular momentum from Earth to the moon. As a result, our planet's rotation lengthens by about 1.7 milliseconds per century, and the moon drifts away by roughly 1.5 inches each year. The change is almost imperceptible within a lifetime, yet over millions of years it accumulates. Days were once far shorter. In the distant future, if this exchange continues long enough, Earth and Moon may become tidally locked, each always showing the same face to the other. Spin does not vanish. It is shared. This quiet slowing is not unique to Earth. Mercury is locked in a 3:2 resonance with the Sun, rotating 3 times for every 2 orbits. Venus rotates so slowly and in the opposite direction that one Venusian day lasts longer than its year. Across the cosmos, gravitational interactions steadily trade angular momentum between bodies. Nothing spins in isolation forever. Motion migrates. On a grander scale, our Milky Way rotates once roughly every 230 million years. The Sun, carrying Earth and the other planets, travels at about 500,000 miles per hour around the galactic center. Yet even galaxies are not eternal whirlpools. Over billions of years, gravitational encounters redistribute their spin. When galaxies merge, as the Milky Way and Andromeda are destined to do several billion years from now, their elegant spiral arms will likely dissolve into a more rounded, elliptical structure. Angular momentum will not disappear, but it will spread outward into dark matter halos and intergalactic space. The organized rotation of spirals becomes the slower drift of a larger system. Those dark matter halos are crucial in this story. Though invisible, dark matter makes up about 85% of all matter in the universe. When we include dark energy, which drives cosmic expansion, the overall composition becomes roughly 68% dark energy, 27% dark matter, and only about 5% ordinary matter. Everything we see, stars, planets, oceans, and ourselves, belongs to that small visible fraction. The rest is unseen structure. Dark matter forms vast halos around galaxies, providing additional gravity that keeps rapidly orbiting stars from flying away. Without it, the spin of galaxies would tear them apart. Rotation and gravity remain balanced because of matter we cannot directly observe. But even this balance will not last forever. As the universe expands under the influence of dark energy, galaxies drift farther apart. Over unimaginable spans of time, star formation will cease. Existing stars will exhaust their nuclear fuel. White dwarfs will cool, neutron stars will dim, and black holes will dominate. Rotation will persist, but it will grow increasingly isolated in a darkening cosmos. In 1974, Stephen Hawking showed that black holes are not completely black. Through quantum effects near the event horizon, They emit faint radiation, now called Hawking radiation. Over incredibly long periods, far beyond the current age of the universe, even black holes will evaporate. As they radiate away energy, they also lose angular momentum. The most powerful engines of spin in existence will gradually fade. Physicists call the ultimate scenario heat death. In that distant epoch, energy becomes evenly distributed. There are no temperature differences left to drive motion, no gradients to power stars, no contrasts to sustain organized rotation. Motion does not strictly disappear. Angular momentum is conserved, but it becomes so diffused that structure dissolves. Spin survives mathematically, yet without concentrated systems to express it, the universe approaches stillness. And yet, even in this vision of cosmic quiet, something profound remains. Angular momentum cannot be destroyed, can only be transferred. The slowing of Earth feeds the Moon's orbit. The merging of galaxies spreads rotation into larger halos. The evaporation of black holes releases energy into radiation. Motion is never erased. It is redistributed. Time itself is deeply woven into this redistribution. The second is defined not by Earth's rotation anymore, but by atomic transitions. Specifically, 1 second is defined as 9,192,631,770 cycles of radiation corresponding to the transition between two hyperfine energy levels of the cesium-133 atom. That number anchors our modern timekeeping. Atomic clocks count these oscillations with extraordinary precision. Yet even this definition rests on spin. The quantum property of particles, intrinsic angular momentum, determines the energy levels within atoms. Without spin at the atomic scale, there would be no stable transitions to measure, no reliable seconds. So from neutron stars to black holes, from galaxies to atoms, spin governs duration. It curves spacetime in relativity. It structures energy levels in quantum mechanics. It defines both cosmic epochs and the ticking of laboratory clocks. When large-scale rotations slow, atomic spin remains. When galaxies merge and stars fade, particles still carry intrinsic angular momentum. Take a gentle breath and consider this continuity. The universe began nearly 13.8 billion years ago with fluctuations that carried angular momentum. That motion cascaded into galaxies, stars, and planets. It shaped days and seasons. It bent time near black holes. It defines the second in atomic clocks. Even as large structures slow and fade, the smallest scales still vibrate with inherited spin. Motion is never truly lost. Changes form. It migrates from massive systems to microscopic ones, from organized spirals to diffuse radiation. And somewhere within that vast redistribution of angular momentum, another kind of structured motion has emerged, the organized electrical and chemical activity we call thought. As we continue turning with this story, the question gently rises. If everything that exists is motion arranged into patterns, could awareness itself be one of those patterns? A moment when the universe's rotation becomes conscious of its own flow. If motion is never destroyed, only redistributed, then it lives on in every scale of reality. including within you. The same conservation of angular momentum that governs galaxies and black holes also governs atoms. Even when massive systems fade into the quiet diffusion of heat death, particles retain intrinsic spin. In quantum mechanics, spin is not a tiny ball physically twirling. It is a built-in form of angular momentum, an internal property woven into the mathematics of existence. Electrons, protons, neutrons, each carries this quantum rotation. It determines how particles align in magnetic fields, how they bond into atoms, and how atoms build molecules. Without spin, matter would not assemble. Without spin, there would be no chemistry. The second, our most precise measure of time, is defined by the cesium-133 atom. When an electron within that atom transitions between two specific hyperfine energy levels, it emits radiation that oscillates exactly 9,192,631,770 times per second. Atomic clocks count those oscillations. They do not rely on the turning of Earth or the orbit of the Moon. They rely on quantum spin and electromagnetic interaction. Every second that passes for you is calibrated by angular momentum at the atomic scale. This is where relativity and quantum physics quietly meet. Einstein showed that gravity and motion shape spacetime. Quantum theory shows that intrinsic spin shapes matter itself. The large and the small are linked by rotation. A neutron star spinning 700 times per second bends time dramatically. An electron with half-integer spin determines the structure of the periodic table. One sculpts spacetime, the other sculpts chemistry. Both are forms of angular momentum conserved since the earliest moments of the cosmos. As the universe ages and expands, galaxies drift farther apart under the influence of dark energy. Star formation will eventually cease as interstellar gas is exhausted. Over trillions of years, the bright spiral patterns we see today will fade. The Milky Way's grand rotation, taking roughly 230 million years per orbit, will become part of a merged remnant after its future encounter with Andromeda. Dark matter halos will continue to cradle the remaining structure, but expansion will stretch space between galaxy groups until each becomes isolated in darkness. In that distant era, rotation still exists, but its expression grows subtle. White dwarfs cool. Neutron stars gradually lose rotational energy through radiation. Black holes, once the ultimate symbols of concentrated spin, very slowly evaporate through Hawking radiation. As they emit particles over inconceivably long timescales, they shed both mass and angular momentum. The universe trends toward uniformity. Energy spreads out. Differences flatten. Motion becomes less dramatic, more diffuse. Heat death does not mean the laws of motion fail. It means gradients disappear. Without differences in temperature or density, there is no organized flow. Yet angular momentum remains mathematically conserved. It is simply carried by radiation, by faint particles drifting through vast, cold space. The universe does not forget how to spin. It just expresses that spin in quieter ways. Now return from that distant future to this present moment. Inside your brain, billions of neurons fire through electrochemical signals. Each signal depends on charged particles moving across membranes, guided by electromagnetic forces that arise from quantum properties including spin. Every thought, every memory, every sensation is a pattern of motion. Electrical impulses travel along neural pathways. Chemical gradients shift. Ions flow. Structured movement gives rise to awareness. Consciousness, in physical terms, is organized activity in matter. It is not separate from the laws that govern galaxies. The same angular momentum conserved since the early universe participates in the stability of atoms, which form molecules, which form cells, which form neural networks capable of reflection. In that sense, awareness is built upon inherited motion. Frame dragging showed that Earth's rotation slightly twists spacetime. A rotating black hole drags it violently. But even at the human scale, motion leaves trace effects. Every mass, however small, curves spacetime infinitesimally. Every moving charge generates a magnetic field. The difference between a planet and a person is magnitude, not principle. You are composed of particles whose spins contribute to fields and interactions extending beyond your skin. When you look at the night sky, photons enter your eyes after traveling for years or billions of years. Those photons carry spin as well. Light possesses intrinsic angular momentum. This polarization can be right-handed or left-handed. The ancient radiation of the cosmos, stretched into microwaves, still carries faint patterns of polarization that reflect the universe's earliest motions. When that light reaches you, it triggers chemical reactions in retinal molecules, initiating neural signals. Cosmic spin becomes biological perception. The universe's rotation becomes part of your awareness. In this way, consciousness can be seen as structured motion reflecting upon itself. Matter arranged in a certain pattern becomes capable of modeling its environment, of remembering, of imagining. Memory itself is encoded in physical states, altered synaptic connections, molecular configurations stabilized by electromagnetic interactions rooted in spin. The universe began with asymmetries and angular momentum. Those properties shaped structure. Structure enabled complexity. Complexity eventually produced organisms able to contemplate the origin of spin. Take a slow breath and notice the continuity. The Earth beneath you rotates once every 23 hours, 56 minutes, and 4 seconds. That rotation slightly bends space-time. Your body, anchored to this turning world, carries atoms whose quantum spins define the seconds ticking by. Above you, the Milky Way sweeps through space in a grand orbit lasting 230 million years. Deep in galactic centers, black holes twist spacetime almost to the speed of light. Across all scales, motion persists, and here you are, a temporary but intricate pattern within that motion, able to pause and consider it. The cosmos is not static matter scattered in emptiness. It is movement layered upon movement. From the Planck era's first fluctuations to the quiet ticking of cesium atoms, rotation defines duration. From galactic halos to neural circuits, angular momentum sustains structure. If heat death awaits in some unimaginably distant future, it will not erase the fact that for billions of years the universe spun itself into stars, planets, life, and awareness. Motion was redistributed, not destroyed. And in this fleeting interval, that motion has organized into a mind capable of sensing time's flow. As we move toward the final turn of this journey, we are left with a gentle realization. The universe has never stopped rotating. It has only transformed that rotation into new forms, until one of those forms could whisper back and say, "I am here, and I am turning too." If awareness is structured motion, then every moment of consciousness is a small, local expression of a much older cosmic rhythm. The atoms in your body were forged in ancient stars that rotated, collapsed, and scattered their elements into space. Those atoms inherited angular momentum from stellar furnaces, which inherited it from galactic clouds, which inherited it from the earliest fluctuations after the beginning. Nothing in you is exempt from that lineage of motion. Even when you sit perfectly still, your planet spins, your star orbits, your galaxy turns, and within you electrons occupy states defined by intrinsic spin. Stillness is only harmony within layered rotations. Time, as you experience it, is inseparable from this layered motion. Your circadian rhythm follows Earth's rotation. Your calendar follows Earth's orbit. Your clocks follow atomic transitions. Relativity tells us that time is not universal but local, shaped by gravity and velocity. A clock at sea level ticks slightly slower than one high in the mountains because it sits deeper in Earth's gravitational well. A clock on a fast satellite runs differently than one on the ground. Duration depends on motion and mass. Remove motion entirely, and time loses operational meaning. There would be no oscillations to count, no orbits to measure, no transitions to mark seconds. And yet, even in the distant heat-death scenario where structure fades and energy spreads thin, the laws remain. Angular momentum is conserved, cannot simply disappear. It can disperse into radiation, into faint drifting particles, into gravitational waves that ripple outward across expanding space. The geometry of spacetime will still encode the history of curvature caused by ancient masses and spins. The universe may grow dark and dilute, but its equations will still balance. Motion may no longer gather into brilliant spirals or blazing stars, yet the bookkeeping of physics remains exact. Consider again the cesium-133 atom defining the second, 9,192,631,770 oscillations between two hyperfine levels. That enormous number is not arbitrary. It arises from the electromagnetic interaction between electron and nucleus, governed by quantum rules in which spin plays a central role. If the intrinsic angular momentum of particles were different, chemistry would differ. If chemistry differed, stable matter might not exist. The second you measure is rooted in quantum rotation. Each tick of atomic timekeeping is a whisper of angular momentum conserved since the earliest instance of the cosmos. Now widen the lens one last time. The Milky Way's 230 million-year orbit around its center is one vast cosmic second in galactic time. The rotation of neutron stars compresses time near their surfaces. The ergosphere of a rotating black hole forces spacetime itself to move. GPS satellites adjust their clocks by about 38 microseconds per day to remain aligned with earthbound time. A Across scales, duration is sculpted by motion. There is no independent river of time flowing untouched by matter. There is only space-time responding to energy and spin. From that perspective, consciousness is not outside physics. It is an emergent pattern within it. Neurons fire because ions move. Ions move because electromagnetic forces act. Those forces depend on particle properties, including spin. Your thoughts are not static objects but dynamic processes, electrical oscillations, chemical exchanges, synchronized activity across networks. They unfold in time because time is defined by motion. The universe's ability to host awareness arises from the same principles that let stars rotate and black holes twist spacetime. You might imagine the cosmos as a vast symphony of angular momentum. Some notes are thunderous. Galaxies colliding, pulsars spinning hundreds of times per second, black holes merging and releasing gravitational waves. Some notes are gentle. Earth's steady rotation, the quiet ticking of atomic clocks, the oscillations inside a single atom. And some notes are intimate. The patterned activity in your brain forming a memory or a dream. All of them are variations of motion redistributed across scales. Even if, far in the future, energy differences flatten and stars fade, there will have been this long era of structured rotation, billions of years in which angular momentum assembled matter into complexity. That complexity became life. Life became reflective. Reflection became science, capable of tracing rotation back to Einstein's equations in 1915, to Roy Kerr's solution in 1963, to the observation of black hole shadows in 2019 and 2022, to the confirmation that even Earth drags spacetime by a tiny fraction of a degree each year. These discoveries are themselves patterns of motion in human brains, encoded in books, signals, and memories. The universe investigating its own curvature. Take one more slow breath. Feel the quiet steadiness beneath you. Earth turns at roughly 1,000 miles per hour at the equator. It circles the Sun at about 67,000 miles per hour. The Sun orbits the galactic center at nearly 500,000 miles per hour. The galaxy drifts within a cosmic web shaped by dark matter and driven apart by dark energy. Beneath all of that, electrons occupy quantized states defined by intrinsic spin. There is no absolute stillness anywhere in this chain. There is only motion layered so smoothly that it feels calm. And within that calm, awareness flickers. Perhaps consciousness is simply motion organized into a form that can remember previous states and anticipate future ones. A localized whirlpool in the larger ocean of spacetime. The universe does not need an external observer. Through complex arrangements of spinning particles, it generates observers from within. In that sense, you are not separate from the cosmic rotation. You are one of its temporary expressions, a brief, luminous pattern in a vast field of conserved angular momentum. If you've stayed until this final turning point, type 4 in the comments and let me know what time it is where you are listening. Before we let this final rotation settle into quiet, pause for a moment and imagine the full arc of what we have traced. From Einstein's realization in 1915 that gravity is geometry, to the confirmation that even Earth drags spacetime by a fraction so small it takes a year to measure, We have followed spin from the subtle to the extreme. We have stood conceptually beside neutron stars rotating hundreds of times per second, where time slows under crushing gravity. We have hovered at the edge of rotating black holes, inside ergospheres where space itself cannot remain still. We have watched satellites gain 38 microseconds per day simply because they move faster and sit higher in Earth's gravitational field. Each example whispers the same truth. Motion does not happen inside time. Motion helps create time. Then we widened our view to the cosmic scale. The Milky Way completes one orbit roughly every 230 million years, carrying our Sun and Earth with it. Galaxies themselves are stabilized by vast halos of dark matter, which accounts for about 27% of the universe's total energy content, while ordinary matter is only about 5%. The remaining 68% is dark energy, driving expansion and gradually stretching the cosmic web. In this composition, visible stars and planets are a minority expression of deeper, invisible structure. Yet even that invisible structure participates in the same law. Angular momentum is conserved. When galaxies merge, their graceful spirals dissolve, but their rotation does not vanish. It spreads into larger, rounder systems. When stars collapse into neutron stars or black holes, their spin intensifies, preserving angular momentum as size shrinks. When black holes slowly evaporate through Hawking radiation, predicted in 1974, they release energy and shed spin across unimaginable timescales. In every transformation, motion is redistributed, not destroyed. The far future may approach what physicists call heat death, where energy becomes evenly spread and temperature differences disappear. Without gradients, organized motion fades. There are no more bright stars to mark cycles, no new structures forming from collapsing gas clouds. Yet even in that quiet expanse, the equations remain balanced. Angular momentum still exists, carried by radiation and particles drifting through expanding space. The universe may grow cold and diffuse, but it does not break its own rules. Now bring the scale inward again, back to the atom. The second that structures your day is defined by 9,192,631,770 oscillations in a cesium-133 atom. That frequency arises from quantum energy levels shaped by intrinsic spin and electromagnetic interaction. Your clock, your calendar, your sense of duration all depend on rotational properties embedded in matter. The same principle that allows a pulsar to sweep beams across the galaxy allows an atomic clock to tick with precision. Vast and microscopic are connected by the conservation of angular momentum. And then there is you, a living system composed of atoms forged in stars, stabilized by quantum rules, arranged into molecules, cells, tissues, and neural networks. Your brain's activity is patterned motion. Ions crossing membranes, electrical potentials rising and falling, synchronized oscillations across billions of neurons. Each thought is a temporary configuration of energy and matter. Each memory is a physical change in structure. There is no need to imagine consciousness as something outside the universe's laws. It is what those laws can produce when motion becomes sufficiently organized. If spin defines the second, shapes gravity, and sustains structure, then awareness is one of its most intricate consequences. The universe began nearly 13.8 billion years ago with fluctuations carrying angular momentum. Those fluctuations grew into galaxies. Galaxies formed stars. Stars forged elements. Elements formed planets. On at least one planet, chemistry became biology. Biology evolved nervous systems capable of reflection. Reflection became the ability to ask where motion came from and where it is going. In that sense, consciousness is structured motion looking back at its own origin. Not mystical but physical. Not separate but continuous. The atoms in your body are still turning in accordance with the same conserved quantities that govern the early universe. The planet beneath you rotates. The galaxy above you turns. The space-time around you curves slightly under Earth's spin. The atomic transitions in your clock count cycles defined by quantum angular momentum. Layer upon layer, motion builds the experience of now. Perhaps the deepest calm comes from recognizing that nothing in this chain is arbitrary. There is coherence from the smallest scale to the largest. Rotation was not added later. It was inherited from the beginning. It shaped structure, bent time, sustained galaxies, powered stars, and stabilized atoms. It allowed complexity to emerge. It allowed this moment. So as you rest, imagine the universe not as a static backdrop, but as an ongoing dance of conserved motion. You are not outside that dance. You are one of its patterns. A brief, luminous configuration of spinning particles, aware for a while of the greater turning that carries you. The Earth will continue rotating tonight. The Milky Way will continue its slow orbit. Neutron stars will pulse in distant darkness. Black holes will twist space-time in silence. And inside you, atomic spins will keep defining the seconds as your thoughts drift gently toward sleep. If you've stayed until this final turning point, type 4 in the comments and let me know what time it is where you are listening.